Alright, so we are asked to prove, um, given that 1c0 over x minus 1c1 over x plus 1 up here is equal to 1 factorial over x groups of x plus 1. This was proven on a previous question. And like these are like some facts that we are given. So that k plus 1cr is equal to kcr plus kcr minus 1. That's one equation. K plus 1c0 is the same thing as kc0. And k plus 1 ck plus 1 is equal to kck. This is, well, where you can prove these by using the Pascal's triangle, which I'm not going to get into here. So we're asked to prove by induction that nc0 over x and this whole big mess. Yeah. Okay, so how induction works, we prove first for n is equal to 1. Okay, so for n is equal to 1, starting with n is equal to 1, so for n is equal to 1, we get 1c0 all over x minus 1c1 over x plus 1 is equal to what, 1 factorial over x groups of x plus 1. Wait a minute, this was proved already earlier. So then, yeah, we already have that with us. So for n, so therefore it's true. Write this across. Therefore, true for n is equal to 1. Okay, not too hard there. Assume true. That's the second part. Assume true for n is equal to k. So wherever we have an n, we just substitute k. Not too hard. Yeah. So I'm just going to take a little detour, shortcut sort of thing. kc0 over x minus, there's a minus there, right? Okay. kc1 over x plus 1 dot dot dot. You get the gist of what goes on. Plus minus 1 to the k, kck k all over x plus k is equal to k factorial all over, now we just get x plus 1 dot dot dot, and we get the gist of it. And we get x plus k. Okay, not too hard there. Okay, this should be closer. Okay. As I was saying, we assume true for n equals k, and so this is my assumption. What I'm going to do from here is I'm going to let x is equal to 2. I'm taking a specific case here for once. So then I get kc0, because remember, this is true for all my assumption is working for all x, right? So I'm just going to let x equal to a specific value. kc0. Oh, no, wait. Is it kc? Yep, x is equal to 2. Pretty sure this is right. Anyway, over 2 minus kc1 over what? 2 plus 1, so that's 3. I can do easy math, right? Okay, plus minus 1 to the k. That is the usual kck. Now this is just, instead of forget that, I'm gonna just take the denominator. It really doesn't matter here. 2 plus k is equal to what? K factorial all over 2 times 3 times so on, 4, 5, so on, all the way up to x plus, no, not x. Now I'm subbing x is 2, so that's 2 plus k. Okay, so this is somewhat similar. This is the same thing as what 2 plus k factorial. Can you see that? Because, well, 2 times 3 and so on, that can be taken as times 1 as well if you need to. But we can also omit, or just take away, leave out that one bit. So then I can say k factorial over what? This is k plus 2 factorial over 1 factorial, because the 1 factorial isn't explicitly there, and 1 factorial anyway is 1, which doesn't really matter anyway. So I can just ignore that for now. This thing is just equal to 1 over k groups, no, k plus 1 groups of k plus 2. I'm not going to expand this because it's too bothersome and I'm way not too bothered for this. Alrighty. Next up, what? Okay. So now this is my assumption. This is my extension of my assumption. Not very hard. Okay. Now the third part that we're trying to get at is prove for n is equal to k plus 1. Alrighty. So what this means is k plus 1 c0 over x plus k plus 1 c1 over x plus 1. And you get the gist. Plus minus 1. I'm going to take the second last term, so which is the k plus 1 ck. The only reason why I'm doing the second last term is so I don't lose track or I don't make any mistakes. So that's plus k there, and then plus, now we're doing the k plus 1th term. K plus 1, c k plus 1, all over x plus k plus 1. Now I'm proving this is equal to, now I'm subbing k plus 1 now, so that's k plus 1 factorial all over x times x plus 1, and so on. You get the pattern. X plus k plus 1. Alrighty, that's cool. Now what? Let's start with our left-hand side, right? LHS is equal to. Now what can I do with this? Okay, now instead of everything being the k plus 1 up on the top, let's just turn them all into k's. The reason why I want to do this is now I can start interacting with my assumption. That's what makes my assumption useful. So I'm going to substitute k plus 1 is, make these all into k's. And how I can do this is by using my assumptions, or what I'm given earlier. See how I have a k plus 1 starting off, and they turn it and break it down into k's. This is also done in all three, and that's how I use them. So k plus 1 c0 is just the same thing as k c0. So I get k c0 over x plus, now this one, k plus 1 c, now for any value r, k plus 1 cr is k cr plus k cr minus 1. So then, so then if r is 1, that means it's just k c1 plus k c, wait, why is this a plus? This shouldn't be a plus. My bad. Scratch that, that's a minus. Okay. kc. Now instead of r minus 1, so that's 1 minus 1, which is 0. All over x plus 1. Plus, well, I'm going to do the next few terms so you sort of see a pattern. kc2 plus kc1 all over x plus 2 minus kc3 plus kc2 over x plus 3, and so on. Plus, okay, I'm going to skip this term. I'm just going to go straight to this. Okay, there's 1 there anyway. Minus 1, k plus 1. Now, k plus 1 c k plus 1 is the same thing as k c k. There. So I'm going to substitute that in. K c k all over x plus, now instead of k, it's k plus 1, remember? So remember, I just substituted from here to get into there. So that's just k plus 1. There. Okay, that's cool. Now what can I do with this? What I can do with this is, now each of these fractions, these composite fractions, I can split into like this part and this part, like split it into 2 parts. Yeah? What becomes really useful from this is I'm going to collect all the first parts together. Okay, so then I get kc0 over x, so I get this initial thing, minus kc1 over x plus 1, plus kc2 over x plus 2, and you get the gist. ... now I'm going to leave out this part, so I'm going to go with the second last part, which is this guy. This middle guy that I left out. Whoops. Okay, so then that just becomes kck. Do you see how, remember how we reduce this by 1, and we keep this, and then add that to reduce by 1, and that reduced by 1. Remember, like, that's the pattern that you can follow along. I'm guessing you can see this. Plus x plus k. Now that is one set. We haven't accounted for everything. Remember, this is a finite set, so this can work perfectly fine. If this is an infinite set, this doesn't really work, just saying. But that's out of this. Anyway, so I get kc0 over x plus 1 plus kc2, not kc2, k plus kc1. I'm taking all the right bits now. Okay, so now I already used up one of these, and I didn't use up one of these, so I'm going to put that in as well. This guy in, okay? So kc1 x plus 2 minus, wait. I factor a minus, so this minus goes away, so then this is a plus. It means this guy got to be a minus. This guy got to be a plus, so that's a kc2 over x plus 3. So you see now, the 0, 1, 1, 2, this is 0, 0, 1, 1, 2, 2. So this kind of aligns perfectly. This doesn't. So, you know, that's just the pattern to notice. This is minus 1, k plus 1, kck, all over x plus k plus 1. Alrighty. Why this is useful? This left bit I can substitute, because this is exactly the same thing as my assumption. Take a look. Where is it? Up here, okay? kc0 over x minus kc1 over x plus 1 and so on is equal to k factorial over that thingo. So I can substitute straight in. So I just get k factorial all over x groups of x plus 1 x plus k. That's cool. But then I got this mess. Ew. X plus 1. It's such a pain. I'm gonna do minus kc1 x plus 2. I'm gonna leave this as a as minus 1 k plus 1 kck all over x plus k plus 1. Alright, that's cool. You know what's really cool about this now, right? Now what I'm gonna do, this I'm going to substitute a specific value of x. I'm gonna let x is equal to, instead of 2, I'm going to let it equal to 1. Why this is cool, right, is now I can, how about you see what happens anyway. This thing becomes, k factorial over, well, I could, this just becomes k factorial anyway, because it's just 1 times 2 times 3 times, and so on. That's also k factorial, as you can see, I think. There's no k factorial, this is k plus 1 factorial. Plus 1 factorial. Because this last term becomes k plus 1, which is k plus 1 factorial. Doesn't really matter. Okay, this left bit, when I substitute, right, I get kc0 over, now I get 1 plus 1, which is 2, minus kc1 over 3 plus minus 1. Instead of k plus 1, this becomes a k, my bad. Because now we used up one of those to factor out, right? So that's just a minus 1 to the k, kck, over what? Now it's a 1, so that's 2 plus k. Now what's so cool about this right-hand part, right, is you see this assumption where let x equals 2. This is where this comes in. kc0 over 2 minus kc1 over 3 plus plus minus 1 to the k, kck over 2 plus k, is equal to 1 over k plus 1, k plus 2. Okay, that's cool. What am I going with this? Where am I going with this? I am going to substitute right in. K factorial over k plus 1 factorial, minus, now this is 1 over k plus 1, k plus 2. What am I doing with this? I'm doing something like that. Why not, actually. This is a cool idea to do. Yeah, should be fine. She'll be right, totally. So then I go along with a k factorial. Now I want a k plus 1 factorial here. Okay, why not make these all both in terms of k plus 2 factorial? K factorial. Now Now this is k plus 2, so I have to multiply by k plus 2 here. That's cool. All over k plus 2 factorial minus, now you want this in terms of k plus 2, so then you have 1, no, you'd have, this thing is the same thing I simplified before, which is k factorial over k plus 2 factorial. K factorial over k plus 2 factorial. Okay, now the same denominator, so then I can have k factorial, k plus 2 minus k factorial all over k plus 2 factorial. What I can do with this, I can make this, now factor out the k, so then I get a k factorial. Now this k plus 2 minus 1, which is k plus 1, all over k plus 2 factorial, which is equal to k plus 1 factorial over k plus 2 factorial. Okay, so what can I do with this? Let's just say see our right hand side as well. So now I'm proving this, right? This thing, right? Now when we let x is equal to 1, right? For this case, when x is equal to 1, then we end up with k plus 1 factorial over what? If I have right hand side, remember we equated x is equal to 1 for our left hand side, so we must do so for the right hand side too. So I get k plus 1 factorial all over. Now I have x plus 1, x plus 2, and so on. X plus k plus 1, which is just the same thing as k plus 1 factorial over k plus 2 factorial, which equates. These both are equal. Therefore, LHS is equal to RHS. Kind of. Reason being is we only specifically allowed for x is equal to 1. So for x is equal to 1. So then, you gotta prove it for all x's as well, or all integer x. But for our case, you kind of get the idea of how to jump across between these two. So for x is equal to 1, to work with all integer x, this works. But I'm guessing this would pick up most of the marks, if not all. I hope this is satisfactory. But this is like the general idea of how you would do this sort of question. Yeah? Alrighty. See ya.